Okay, so my approach to this was quite different. My approach to this was, okay, so we don't really know what the theory of smell is, yeah? But there are certain things that we do notice about molecules that have smells. And the first, this is on page 17 in your books. The first is that there seems to be an inverse relationship between molecular size and impact. So if we look at molecular weight, that's the mass or the size of the molecule, if you like. What we find is that there are no molecules known that have smells above 400. So that's molecular weight. So the impact is 0. And that sort of makes sense because the bigger a molecule, it has to evaporate to get into our nose. So that's one aspect. So big molecules can't produce vapors that we can smell. Yeah? But we also notice that if we get very small molecules, they have very high impacts. And then in the mid-range, linalool, if we talk about this range in around about 180, we find they have an impact of around 100. So what we end up with is a curve like that. Yeah? So big babies move slowly. Yeah? So they have less impact. Smaller molecules evaporate, yeah, reach our olfactory bulb quicker, have more impact. Sort of makes sense. So that's the first step we look at. We look at how big is this molecule that we're looking at. The second thing that we look at is its polarity. What that means is its solubility or its affinity. What we find is that materials that are 100% soluble in water do not have smells. Salt, sugar. Do they have smells? Well, actually, I can smell sugar in coffee and things because I don't take sugar in coffee, so I can smell it. But I'm not smelling the sugar. I'm smelling the non-sugar part of the sugar, yeah, the flavour part of the sugar. So brown sugar has a much stronger flavour because of the contaminants, not because of the sugar part. Yeah, it's the other things that have the smell. But the sugar itself, yeah, has no smell. Salt has no smell. So there seems to, and we find that the more something is insoluble in water, the stronger its impact tends to be. Yeah. And there's one particular group that we get on a chemical structure, and it's the OH group. Yeah. That makes things have an affinity for water. Yeah. A hydroxyl group. And for the names of materials, it's also the alcohol group. Yeah? So if you remember, I said about linalool was the alcohol found in linalool berries, or not. Yeah? The OL indicates it has that group. Yeah? But bear in mind that this is what we call a functional group. This is like an arm on the molecule. So if I have a really, really big molecule, yeah, big body, yeah, and I just have one little OH group, then it's not going to affect the solubility that much. It's going to make it slightly soluble, but not completely soluble. But if I have a small body, yeah, and an OH group, then it makes it completely soluble. So ethyl alcohol, yeah, H. Normal alcohol, alcohol you get in whiskey and vodka, yeah. The OH group is quite a big portion of the molecule, so it makes it 100% soluble, yeah. When we get phenyl ethyl alcohol, so that's the ethyl alcohol, but because we've got a bigger molecule, yeah, it's less soluble. So phenyl ethyl alcohol is 100% soluble in water. So phenyl ethyl alcohol is only about 2%, 2.5% soluble in water. So as the body gets bigger, the comparison between the OH groups and the rest of the molecule, so the solubility goes down. So when we're looking at this system, we look at the solubility or the polarity. The polarity is just a word that chemists use more than as opposed to solubility. So the next step we look at is the body of the molecule. And you see I've drawn it as a big spider, but I'll draw it as a... Okay, so that's the body of the molecule. The body of the molecule is like my body. The body part of me doesn't do a lot of interacting with the world. Yeah? The body mostly just makes the mass of the molecule. Yeah? I'm not saying it has no effect. It has some effect, obviously. Yeah? Same as my body has some effect and some interaction. But it's much less than my hands or my feet or my appendages. So if we look at the structure of a molecule, we have the body of the molecule, and then we have these arms and legs, which we call functional groups. But it's the functional groups that catch on to other molecules. They catch on to the receptors in our nose, yeah, and give more effect on the smell. So I'll talk about, not in too much detail, yeah, because you'll get some of the detail as you do the exercise. But there are two basic types of body. You get cyclic bodies. That's where the molecules attached as a ring, yeah. And you get acyclic bodies, yeah, where they're not attached, yeah. These are called alkanes. These ones are called terpenes. And these ones are called phenols, for example. Yeah. You can get cyclic terpenes. So I'll give you an example. Linalool is an acyclic terpene. Yeah, it's not a cycle. It has an alcohol group on there. So that's what something like linalool looks like. But if we get a join here, an OH, that looks more like menthol. So interestingly, when we get terpenes, we get this metallic sort of herby character. Yeah. When it becomes cyclic, we get a cooling effect. Yeah. With these ones, what we find is that when we get just one or two bonds, the impact is very, very high. But as the chain gets longer, so the impact goes down. Any questions? Or is it just like blank? Just let it bubble in the back of the mind as you're doing the exercise. Yeah. Now sometimes we get, you'll see in group 3 it says specific structures. There are specific combinations that we get that always give a certain result. Yeah? And examples of these are phenyl ethyl. Phenyl ethyl, phenyl is like the P in the tray, yeah, medicinal. But ethyl, like ethyl alcohol, gives a sweet character. So what we get is a sweet medicinal character, and it always means rose. Whenever you see the name phenyl ethyl in the name of a chemical, always smells of rose. Carries this particular character across. Phenyl acetate. Acetate comes from what acid? Acetic acid. What's acetic acid in English? Vinegar, yeah? So it has a very sour smell. Most fruity notes have this acidic quality. So when we have an acetate on something, it makes it a little bit fruity. So we have this sour fruity character. What was phenol? Medicinal. Always smells, because of this sort of combination, this clash, always smells of honey. So whenever you see the name phenylacetate, yeah, in something, yeah. Sorry? Okay, so when we have phenol, it sort of indicates that it's on its own, yeah? When we have the YL, it indicates it connects to something else, yeah? So it's an indicator to the name. It's like grammar, yeah? Chemist grammar, yeah? YL means it connects to something else, yeah? So this system that I'm teaching you is Lego bricks. So if we had a chemical called phenyl ethyl phenyl acetate, what would it smell of? honey rose. Yeah. And that's exactly what it smells like. Yeah. So you'll see on, oh no, I'll do this in a minute, yeah. Then, so these could be, this is actually a functional group, the phenyl acetate. The phenyl ethyl is the body. Yeah? Phenyl ethyl, phenyl acetate. The functional groups, like I said, is where the more interesting stuff happens. These are the arms and the legs that we got on a molecule. Yeah? And if it's a straight chain with one carbon, with one carbon, it's a formate. So, CHOOH, that's from the acid. Benzyl formate, something like that. I'm actually sure that's not quite true, correct. A formate. Formates always have, anybody know formaldehyde? Used for bottling dead animals in the science lab. How does it smell? Awful. Any other description? Incredibly dry. It's incredibly drying on the throat. Yeah. So if you drink methyl alcohol, which also has one carbon, it's incredibly drying on the throat. Wood alcohol has a woody, very dry character. So, what would phenyl ethyl formate smell like? Dry woody rose. Bingo. Yeah. If it has two carbons, it's called an acetate. Yeah, these are functional groups. So these are produced from reacting formic acid with phenyl ethyl alcohol. The alcohol gets knocked off. The formate takes its place. Yeah, the formic acid takes its place. It becomes phenyl ethyl formate. Acetate comes from vinegar. So what would phenyl ethyl acetate smell like? Fruity rose. Who knows what phenyl ethyl acetate smells like? Do you know it? No? It smells like a fruity rose. Yeah. The next one up is propionate. Sorry? Yeah, C3, sorry. 3 carbons, yeah? So propionate from propionic acid is a little bit sweeter than the acetate. So phenyl ethyl propionate is less fruity and a bit sweeter than the acetate. The next one up is C4. Butyrate. Butyrate is from which acid? Butyric acid. Does anybody remember from day one what group butyric acid falls in? The ABCs. In the dairy, yeah, because it's a buttery or a cheese-like smell. If you get cheese and you leave it in its packet in the warm, it gets that horrible yellow liquid around it. Very high in butyric acid. Yeah, that's the character of butyric acid. So, what does phenyl ethyl butyrate smell like? It's more sort of creamy, a sort of a creamy rose, yeah? A sweet, fruity, creamy rose, yeah? valerate. Smells, it becomes milky and a little bit winey, sharp. So phenethyl valerate is a sweeter, fruity, a bit creamy, but a bit like sour cream, more like sour cream than the butyrate. Some of our functional groups are rings from salicylic acid. Salicylic acid, what group would that likely to be in? Sorry? Medicinal, close, one letter down. The orchid, yeah. Yeah, the salicylates give you, it is a medicinal smell, yeah, but it gives you this orchid character. Now, if we look back at the bodies, so salicylate has this orchid character. And if we look back at the bodies, some smaller bodies, the smallest body we can get is methyl, which is a little bit like that formate. It's a little bit dry, it's a little bit harsh. Methyl salicylate. So who knows what methyl salicylate smells like? Harsh orchid. But actually we know it as wintergreen. Wintergreen or methyl salicylate, used in tiger balm, yeah. Used in counterpain, yeah, that's methyl salicylate. Sports injury things, yeah. So that's very harsh. It's harsh because we have this big functional group compared to a small body. So here we have like big arms with a very tiny body, one carbon, yeah. If we go to ethyl salicylate, which is 2 carbons, I think it's 8. Yeah, 8 carbons. So it's comparatively. Don, you're the chemist. Salicylate, how many carbons? Okay, we'll come back to you. We'll confirm. Yeah, I think it's 8. Okay, so methyl salicylate. So ethyl salicylate. That body is now a little bit bigger. Ethyl alcohol compared to methyl alcohol is sweeter. So what we have is counterpain, but a little bit sweeter. Yeah. Ethyl, butyl. We never see the third one, but fourth one is butyl salicylate. Yeah. When we get to butyl salicylate, sorry? Is the functional group. It's because it's from salicylic acid. Salicylic acid is the stuff you put on warts and corns to melt them away. It's a white paste you get from the pharmacist. Yeah.
Sorry, how did you describe ethyl salicylate?
As a slightly sweeter version of the methyl salicylate. So it's a bit sweeter than the counterpain. When we get to butyl salicylate, what happens now is the orchid character starts to become obvious as a floral note. Yeah? So this now becomes like a fresh orchid. Butyl has a slightly milky, fresh character. When we go to C5, amyl salicylate, it's now becoming more and more floral. Yeah. And then we come to this really interesting one at C6, hexyl salicylate. And hexyl, yeah. Does anybody remember the name cis-3-hexanol? Which group was that in? In green. Yeah. Hexyl, whenever you get hex in the name, it's always green. So what we have here is we have like a green orchid character. And it's like the top note of an orchid flower. It's like it's got the greenness as well. Okay. I've never actually seen it. I've never seen propyl salicylate. So yeah. Sorry? Propyl, propyl. Propyl, yeah, sounds a bit. Now, there aren't that many words to remember. So what we have on the next 2 pages are a table of words that will cover probably 90% of the aroma chemicals you will come across. So if you have the chemical name, yeah, you can predict what the smell is likely to smell like. Yeah? Now, if you've read The Emperor of Scent, yeah, you'll see that it's a battle between, you know, not good and evil, but Dr. Luca Turin, yeah, and the establishment, the perfumery establishment. The perfumery establishment is represented in the book by Charles Sell, who is a big proponent of the shape theory. Yeah. I've met him, he's a very nice guy, yeah, but he's very, very traditional sort of, yeah, yeah, stubborn, yeah, yeah, but then I'm stubborn, so. I forgot what I was going to say. Where was I? Sorry? No, he didn't, of course. No. I've not much. Yeah. Yeah, that's another story. But where was I? So you have a table here, yeah, of what names and what the smell is, what the molecular weight is, yeah. So what we'd like you to do is to go through a range of aroma chemicals. The sheet we hand you out will have the names. And what I would like you to do is to look up and predict what the smell would be. So you have to take into account the size of the molecule, does it have an OH group on it, an alcohol group on it? How big is that alcohol group compared to the rest of the molecule? Yeah. Its function, its body. Is it a specific structure? So you'll have phenol, but then you'll have phenyl ethyl or phenyl acetate. So check there isn't, so once you've found phenol, make sure there isn't a phenyl ethyl, yeah, and then compare that. And then check the functional group, yeah, and then what you do is you write down a description based on that. So if it was a small molecule with an OH group, you probably have the word something like soft, yeah, to start it off with. Yeah. Oh, I remember what I was trying to say when I talked about Charles Cell is actually what you're doing now from the current thinking about shape theory is impossible. Yeah? So if it works, it points more towards vibrational theory. But there is a shape factor that comes into it because if the molecule is too big, it can't attach to the receptors. So there is a certain amount of shape that does come into it because if a molecule is too big, it never gets to your nose. Yeah. The best way to deal with these is to pull these sheets apart if they're attached. Yeah? Yeah, yeah. So, is everybody clear about what to do? Yeah. What you do is go to the white sheet. Yeah. You see the group A. Read the names. Look up on the two sheets with the coloured bands on them. The bodies are shown in blue. Is it? In blue. Yeah. And the functional groups in red. Pink. Yeah. And you'll see that there are some things with dots there. These are things called isomers. I won't go too much into that, but there's some effect on the smell, but generally the character of the smell doesn't change that much. It's a different type of smell, different tone, but basically the smell is similar. Yeah. So the first one is aldehyde C8. So in brackets there it says octyl as well. So you want octyl aldehyde. Yeah. So if you go down the column of the blue and look for octyl, what does octyl smell like? Hard citrus. And aldehyde? Harsh chemical. So harsh chemical citrus aldehyde. Yes, so you add up the two to get the total molecular weight. And does it have any OH groups? No, no. Yeah, so that means it'll be fairly strong. Yeah. Has an OH group, it will become softer. Solubility, does it have an OH group? A hydroxyl group? Yep.
You in the predicted smell, you mentioned 10% in DPG.
Yeah.
That's just going to dilute it.
Yes. That gives you a clue. It gives you a clue that it's probably a strong material, yeah, or it's a solid material, yeah.
Can I ask a question about where you've got here the body, the C carbon?
Yeah.
So presumably you have to take that into account with the aldehydes.
Well, the C8 actually means the same as octyl.
Oh, it does. Okay, so
Yeah,
that's, you wouldn't add that.
You don't need to add on that. Yeah. Yeah. No, just those A to A. All the way, that 5. Yeah, just those 5.